Okay. So we've been talking about looking about sampling distributions, but we really haven't shown you what a sampling distribution really is. So with a sampling distribution, it's not too different from when we were doing any kind of other probability distributions. So we've been doing probability distributions all along, or not all, well, all along. We just haven't always called them that, but we've been talking about probability distributions of just an x value. So we have an x, we have a probability that particular x happens. So in the dice roll, my x's were either 1, 2, 3, or 4 because we're talking about individual die rolls. So the probability of rolling a 1 is 1 out of 25. Probability of rolling a 2, or sorry, is 1 out of 4 or 0.25. Probability of rolling a 2 is 0.25. The 3 also 0.25 and 4 is 0.25. This is a uniform distribution. So I counted something incorrectly a little while back. So I'm going to mention that here. We actually have 64 different samples here. So we're talking about the samples of size 3. We collected 64 possible samples that it could exist, and we found the means of all of them. So what we have here is a whole data set. And this is a data set of means. Well, also, we can do a probability distribution as well. I can do a probability distribution if it's the means. So I'm going to talk about a probability distribution of x bar instead. We'd have an x bar, and now we're looking at the probability of a particular x bar. If we go back over here, we got a mean of 1, which happened 1 out of 64 times. So the probability of 0.16. We had, pick a different color for this, we had is 0.3. That happens a couple times. Only 3 times? Yeah, that happened 3 times out of 64. So the 1.33, well, that has a probability of 0.043. So I can keep on doing this for each number. The only means that we keep repeating is that we have a mean of 100, 1.33, 1.67, 2, 2.33, 2.67, 3, 3.33, 3.67, and 4. Which makes sense because I got numbers 1 through 3. These are the kind of numbers I would expect to get when I average that out. And what you see is we get a probability distribution here. So this is telling me the probability of my mean being 1. So if I take a sample of 3, the probability of the mean is 1 is 0.016 or 1.6%. The probability that my mean is 1.33 is 0.047. So we got ourselves just a regular old distribution. I grab a different color here. We're seeing that we start here, our means keep increasing, or not means, but the probability of those means keeps increasing. And then eventually it starts to go back down. I think I went too far. But that's what we're seeing here, right? We got a 0.016, a 0.047. And we're just looking at those different means down here. Okay. So in the tetrahedral die example, like I said, the population 1, 2, 3, when we roll the die, they each have the same chance. So we would have a uniform distribution. These are still probability distributions. So this is my probability distribution of, I'm going to just shorthand distribution of x. And this is my probability distribution of all those different means. So one of the things to notice here is that the shape of the distribution has changed. So this is going to be a feature that we're going to see a lot when we talk about a sampling distribution. And mostly what we're going to see here is, like I said, the probability histogram of the sampling distribution X bar with sample size 3. It's obtained by the sampling distribution in the previous slide, the one we're talking about right here on the bottom. The probability histogram for the sampling distribution looks a lot more like a normal curve, whereas the probability histogram of the population, so this is my population, and this is my means. We see as the population is uniform, but this starts looking like a normal curve. So remarkably, this is going to happen for pretty much any population. If the sample size is large enough, then the sample mean X bar will be approximately normally distributed. Okay. So I'm going to move to that applet here in a second. Okay. So we're going to go here. And what we see here is that this is what we're calling the parent population. So these are my X values. We got just a normal regular shape distribution here. So I'm probably going to change that in a second. So this right here is that this is going to look at a sample. And then this is going to be the distribution of means of samples. So we're going to start out where we're going to have samples of size 5. So what a sampling distribution is essentially doing this. I just collect 5 items from my sample, and then I get an average for it, and here's my average. So remember that whole part where I said, let me center this right here. One of the things I had said was that I expect that when I collect, samples, just individuals, I expect to get means that are all over the place. So I got some small mean, or not means, sorry, values all over the place. So this is a small X, this is a large X, this is a couple more. But when we average them out, even though they're kind of all over the place, they're pretty close to that mean that we have here for the original distribution. Let me do this one more time. Like I said, we got some big X's, some small, big X's, small X's. We got one that's almost exactly on the mean. And when we average them out, we're very close to the mean again. So as I kept doing this, keep getting samples. You start seeing that this distribution is simple. Sample means it's still pretty centered, but you notice that's very, 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 very close to that center. This line is representing population mean. So like I said, individuals, I expect to be very spread out. The probability of getting very small and large values is pretty decent. But when I average it out and I get a mean, those means, because they're averaging those values, are going to be close to that population mean. Okay. So I'm going to collect several samples. So I'm going to collect 10,000 samples of size 5. To kind of get you the idea what this distribution looks like. And at this point, it doesn't matter how many more I collect, pretty much looking the same. So we notice right here that both means are 16. This is saying that the mean is 16, and this is saying that the mu sub x bar mean of means is 16, which we had mentioned before that should happen. So if I collect enough samples, we expect to see this. Standard deviations. So standard deviation for this population of just x values is 5. And then over here, the standard deviation, the sigma sub x bar, is about 2.25. So remember, if I take 5 and I said I was doing samples of size 5 and I divided by the sample size of 5, 5 divided by the square root of 5 is going to be 2.24. So it's very, very close. Like I said, there is going to be some discrepancies that we're going to see here, that things are not going to always be exactly the same, but they should be pretty close to each other. Okay, so this is what I was talking about, is because I'm getting these samples. These are all not samples. Yeah, these are all samples of a certain size, and I'm collecting all those means of those samples, those X bars, that these X bars should be closer to the mean. That means my spread is much smaller than the spread of the original population. So what we see here is that my standard deviations are going to get smaller and smaller. So let me clear this, but I'm going to leave some of the spread here because we're going to see what happens now if I take a sample of size, let's say 20. Those are larger samples. I'm collecting a lot more data, but we're getting a lot more of it is centered towards that middle. And when we get that average, it's very close to the middle again. More data points, a lot more of them are going to be towards the center of the distribution because we got a lot more probability of that. We add them, we're getting pretty close to the center again. So if I collect several samples, what we see here is that my standard deviation is smaller because when I have larger samples, we expect less variation. So larger samples, less variation. And once again, you're talking about the means. The mean here is 16. The mean here for the sampling distribution is very close. It's 15.99. My standard deviation is going to be 1.13. So if we had used my calculation, that should have taken that 5 and divided by the square root of my sample size, which is 20. We would expect it to actually get 1.12. So we're really close. That is why we end up saying that this relationship and this relationship is true, because with large enough samples, they're very, very close to each other. Same thing here. These are very, very close to each other if samples are large enough, or we have enough samples. Okay. So let's say I have a skewed distribution. No, remember, this is my population of X values. And the mean, I'm trying to look for the right number here. It's right here. I'm slightly off. So the mean of the distribution is about there. I'm like a hair off where it needs to be. This part is going to look at my samples, and this is going to be my sample means. So if my parent population, what I originally start out with, is skewed, we see most of my values, we're getting some that come out here, but most of them really close to the center. We're getting a mean very close to the center. Okay. So we're doing 5 samples at a time. So as you're seeing here, I'm not getting very many numbers that would pop up here. That's not very likely, because most of my numbers are going to be here. So when I average everything out, those means are going to be close to that center. So what we see here is we started out with a population that was skewed. And when I'm using a sample size of 20, what we see is that my distribution of means is looking pretty normal. It's got that symmetric bell-shaped curve to it. Sorry, I was trying to draw that in there. So we're seeing something that's looking normally distributed. Now let me backtrack a second. Let's make smaller sample sizes. So if my sample sizes were just sample sizes of size 2, what we're finding is that those samples don't have, they could be a little more over the place, but they don't have enough. Like with the bigger samples, we have several numbers that are towards the center that pulls everything towards the center. That's not really happening here as much. Sometimes it is, sometimes it's not. Like that one, we got two really close together on this side. I put it right here. So it can't adjust itself for the errors as well. So if I did a small sample size, notice that we started out with something that is skewed. To the right, and now we're still skewed to the right. So when I have a sample of size 2, the distribution of means is still skewed. So what we need to do is any distribution is going to stay pretty much kind of skewed until we find the sample size. As you see, it's still skewed, but not as skewed. We find a large enough sample size that starts to become normal. So at 10, still a tiny bit skewed. 16, a little bit of skew left. And when we hit 20, we still have a bit of a skew, but not as much. And this one almost has no skew to it at all at a sample size of 25. So we can always pick a sample size large enough that it forces our distribution to be skewed. And we actually have one we know works for any distribution. So if a population, like I said, it doesn't matter if it's skewed or what it is. If it's skewed, it could be bimodal. I've done it with bimodal before. It doesn't matter what your distribution is. There is a large enough sample size necessary for the sampling distribution to approximate a normal curve. So my parent population here is skewed. If I do a sample sizes of 3, it might still be skewed. If I do sample sizes of 10, it's a little less skewed. And when I do a sample size of 30, it's almost pretty much exactly normal. So one of the things we have found is that the size of the sample needed to obtain approximately, make something approximately normal distribution of means, there we go, depends mostly on the skewness of the population. In practice, a sample size of 30 is large enough for any. So as we saw, one of the ones I did earlier, like 20 started kind of getting us there, and 25 nailed it. Here we have to get the 30. So you can try different sample sizes and certain sample sizes depending on how skewed or really just how disturbed your data is. There is a sample size that will make your sampling distribution look normal. And we know that at least above 30 usually does it all the time. This gets us to one of the big theorems we have in statistics, which is our central limit theorem. And because we hate seeing central limit theorem all the time, we tend to say CTL, or CLT, sorry. The remarkable fact that the sampling distribution of X bars is approximately normal for a large sample of any distribution is part of one of the most used theorems in statistics. So like I said, we use this a lot because we have a lot of distributions that are not normal, but I know by central limit theorem, I can make their distribution of means normal, meaning that a lot of that stuff that I need a normal distribution for to assess, I may not be able to assess the population, but I can assess a population of means. So if X is a mean of a large, so n's greater than 30, simple random sample from a population with a mean mu and a standard deviation of sigma, then X bar has an approximately normal distribution with a mean of mu sub X bar equals mu and a standard deviation of sigma sub X bar equals sigma divided by the square root of n. We can only really use this if my sample size is large enough that X is approximately a standard normal curve. So the central limit theorem applies for all populations. However, for symmetric populations, a smaller sample size will probably suffice. And also like the skewness of it may make a difference. Also, like sometimes with bivariant data, it won't take a very large sample size. If a population itself is normal, the sample mean X bar will be normal for any sample size. So if my population already started out as normal, it doesn't matter what the sample size is, I'm still going to get a normal sampling distribution of means. All right, so we're going to here decide whether it's appropriate to use the normal distribution for X bar. A simple random sample of 45 is drawn from a population with a mean of 15 and a standard deviation of 3.5. Well, n is greater than 30 because n happens to be 45. That's my sample size. So yes, it is appropriate. And also we know that the mean of this distribution would be 15. And we know that the standard deviation of this distribution is going to be 3.5 divided by the square root of 45. Which in a second here, 3.5 divided by square, oops, just a second there. I just tried to do a logarithm instead. That is going to be approximately the standard deviation would be 0.52. A simple random sample of size 8 will be drawn from a normal population with a mean of negative 16, a standard deviation of 5. So our sample size is 8. It is not greater than 30. And we don't know if the original population is random. If we knew if the original population was normal, we wouldn't need this. We don't know if the population, the parent population, is normal. So these are my problems. So we'd say, no, not appropriate. It is not appropriate to use the normal distribution of X bars to represent this. Okay, and then for the next one, I got stuff on my end, it needs to move around. We have a simple random sample of size 42 drawn from a population with a mean of negative 118, a standard deviation of 24.8. So my sample size is 42. This is greater than 30. So yes, it is appropriate. We'll have a mean for this distribution of negative 1.8 and a standard deviation of 24.8 divided by the square root of my sample size, which is 42. It's going to be 3.83. And then once again, this is going to be the same rule. A simple random sample of size 24 will be drawn from a population with a mean of 35 and a standard deviation of 1.5. So n is 24, which again is not greater than 30. We don't know anything. We don't know this part either. We don't know if the parent population is normal. So no, it would not be appropriate. So we can really only treat a population as, treat a population of X bars as normal if that sample size, like I said, is over 30, or if we know if the parent population is normal, which we're not told that here. So in this case, I can find a mean and standard deviation for my X bars. Here I cannot.